All right, we're going to talk about section 3.3 today, the conditionals and the circuits. So we're going to talk about conditional statements, negations of conditional statements, circuits. So the first thing is a conditional statement, and a conditional statement is a compound statement that's just written in the form of if something, then something. So you could say, if you go to school, then you get good grades. If you are a college student, then you go to Germana. So conditional statements just have the format of if, then. And usually we use a symbolic formation for conditional statements. It's a P arrow Q, which is said P implies Q, or if P, then Q. The P part of the statement is called the antecedent, and the Q is called the consequent. Sorry about that. So also we might have also heard the term that P is called the hypothesis and Q is the conclusion. So there's a truth table for conditional statements. The P implies Q. If both of the parts are true, then your result will be true. If the hypothesis is true, or if the antecedent is true, then the consequent will be false. Then the condition is false. If the antecedent is false and the consequent is true, then the overall result is true. So what we end up summarizing that is that the P implies Q is false only when the antecedent is true and the consequent is false. If the antecedent is false, then P implies Q is automatically true. So let's look at what we have here. It says find the truth value and assume he and R are false and that Q is true. So if we have this statement and we start with that, and this is read, P implies the negation of Q and P implies R. So again, it tells you in the directions that P and R are false and that Q is true. So everywhere that there's a P, we're replacing it with false. And everywhere that there's an R, we're replacing it with false. Everywhere that there's a Q, we're replacing it with true. Not true will reduce to false. For the negation of true is false. So now using our truth tables, false implies false is a true statement. If you start off with something false and you get a false result, that's a valid statement. That's true. And then, of course, using order of operations, we do our parentheses. So false implies false is true again. And then using our truth tables that we talked about in the last couple of sections, true and true is true. So the result of this truth value, or the truth value for this example, would be true. So here we want to decide if each of these statements is true or false. So we're going to analyze the right-hand side of the problem first, or we're going to analyze the parentheses first. 4 is less than 2 is a false statement. So this now reduces to true implies false. And then when we use our truth table information, our truth table information tells us that the results for this would be false. Okay, so let's look at the other example. 8 is equal to 8 is a true statement. So I'm sorry. 8 is equal to 8 is a false statement. 8 is equal to 1 is a false statement. Let's see if I can do this right tonight. Is a false statement. False implies false is a true statement, and so the result of this problem would be true. So the result of our first problem is false, and the result of our second problem is true. So many times it helps to have a truth table. So what we have here is something called a tautology, and a tautology is a statement that is always true no matter what the truth values of the components. So we're going to figure these out by looking at truth tables and figuring out whether we have a tautology. So here we have a truth table. Now what we're trying to do is figure out this part of the problem over here. That was the original statement. So our truth tables are always going to be started off the same way. We have true, true, and then we have true, false, and then we have false, true, and then we have false, false. So the value of P is true, true, false, false, and the value of Q is true, false, true, false. So again, using our truth tables, P implies Q. If P is true and Q is true, is true. If P is true and Q is false, the truth value is false. If P is false and Q is true, then P implies Q is true. So because our problem that we're dealing with over here involves not P, right here, then we need to figure out what not P is our truth table. So if P is true, then the negation of true is false. If P is false, the negation of P is true. So our negation column is false, false, true, true. So now for the next column, what we need to do is focus on two pieces in the chart. I'm going to erase this for a second so we can look at this better. The two pieces that we need to look at are the not P column and the Q column. And we're trying to figure out the OR value or the union value. And what we want to remember is that with the OR value, if one of the two components is true, then our result will be true. So the first time we're comparing true and false. So since one of them is true, the result is true. False or false is false. True or true is true. And false or true is true. So we now have that column of values. So for our last step, what we want to do is focus on two columns in our chart. We want to focus on the P implies Q column and the not P or Q column. And we're looking to see the truth values for that. So when we have true implies true, according to our table, that would be true. False implies false is a true statement. In other words, it always is true. If you start with something false, you'll end up with something false. True or implies true is true. And the last one is true implies true is true. So since the result of this condition is always true, no matter what the starting conditions are, then this is called a tautology. Okay, so here's another statement. If I have the negation of P implies Q, what I'm going to show you with this chart is that the negation of P implies Q is the same thing as P and not Q. So again, we start off our tables the same way with our P and our Q values, and then our P implies Q values. So all of this is the same as the first couple of charts that we've looked at. So for this next column, I'm going to take the P implies Q column, and I'm going to negate it. So that means all of the values are the opposite. So it was true, now it's false. It was false, it's true. It was true, it's false. It was true, it's false. So for the next column, because I need not Q for this part of the problem, I'm going to go through and do the opposites of Q. So true becomes false, false becomes true, true becomes false, false becomes true. All right, our next step, we want to figure out the last part of our problem. So what we're going to do with the last part is we're going to take the P column and we're going to take the not Q column and we're going to apply the AND operation to it, meaning if they both have to be true to be a true statement. So true and false is false, true and true is true, false and false is false, and false and true is false. Okay, and here's our last step. The point of this chart was to show with our chart that P implies Q is equivalent to P and not Q. So now if we look at these two columns of the chart and we compare them, oh, I'm sorry, I hesitated. I thought I wrote something wrong. We're trying to show, let me go back and say that again. We're trying to show that the negation of this is the same thing as P and not Q. So the negation of this is this column right here. I'm sorry, that's where I was confused. So we're showing that these two columns in green are the same. And if you compare the values in these two columns, you'll notice that you have the same values in both of the columns. And so we've just shown that those two values are equivalent. Okay, so we're going to do the same idea here. We want to show that P implies Q is equivalent to not P or Q. So we're going to do this one slightly different. What we're going to do this time is we're going to go through and we're going to negate both sides. So if I start off with the statement that I know is already true, I already know that the negation of P implies Q is equivalent, we're going to use 3 signs there, to P and not Q, or tilde Q. So if I go through this, what I want to do is I want to try and make this into P implies Q instead. So I'm going to negate both sides. So I'm going to negate this entire left side. And if I negate the left side, I have to negate the right-hand side. Okay, so when you negate a negation, it becomes positive. So this cancels out, and I'm just left with the P implies Q. On the right-hand side, if I use De Morgan's law, basically I can think in terms of distributing the negation. So I end up with not P. But remember with De Morgan's law that the and symbol will become an or symbol, and the negation of negation is regular. So again, this is what we did. We started off with a fact that we already know. We just proved on the previous slide that the negation of P implies Q is the same thing as P and not Q. So then if I negate both sides, I end up with P implies Q on the left, and on the right-hand side, using the Morgan's law, I end up with not P or Q. So what I've shown is that P implies Q is equivalent to not P or Q. So now let's figure this into our problems. If you want to do the negation of each of these statements, you're going to apply this information. You have a statement that's in an if-then format. If you ask him, then he will come. So I have P and Q. So in order to negate it, what I'm going to do, remembering what we just did, put this up here. If I have P implies Q, the negation of that is equivalent to P and not Q. So if I want to negate this statement, I can rewrite it with the word and I can negate the Q portion of the statement. So if I rewrite the problem with the word and, I would basically be putting the word and in between him and he will come, and I will be changing he will come to he will not come. So my statement will say something to the effect of, you ask him and he will not come. On the next statement, you have all dogs love bones. So basically you're saying if it's a dog, then it loves bones. So the negation of that would be if it's a dog and he does then, it is a dog and it does not like bones, or it does not love bones. So here's what you have. Again, this is what we did. This is the P part of the statement. This is the antecedent. And if you look up here, this is the antecedent. This is the consequent or the conclusion. This is the conclusion here, but we did not Q. The symbol for and, the word and. Okay, so same thing up here. We have it's a dog is the antecedent, loves bones is the Q, or the consequent. It's a dog is the antecedent, and is the symbol. Does not love bones is not Q. So what we're doing here is we're showing how you can make it a little bit clearer maybe about how circuits work and why things are the way they are. So here's what we have, and if we talk about a basic circuit here, if I have a circuit, okay, and if you think about electricity, in order for something to happen, the circuit has to be closed. In order for anything to go through, this has to be closed for the circuit to flow. So when you're talking about a series circuit, basically you're thinking of P implies Q. In order for this to work, both parts have to be closed. So if you think about being true as being closed, the P would have to be closed and the Q would have to be closed in order for it to be true. So P and Q. Okay, so a series circuit is equivalent to using the word and, or just an if-then statement. A parallel circuit would be equivalent to the word or. So a parallel circuit would be used with or. And what happens here is that when I travel along this path, I can move up, or I can travel down, and I can still get to the same location whether I travel up or I travel down. So a parallel circuit is a representative of the or symbolism, And a series circuit is symbolism of an AND circuit. Okay, so these are just some statements to keep in mind when you're working through these problems. If you have P or Q and R, that's equivalent, if you want to think of it this way as distributing, it's equivalent to P and Q or P and R. And the same thing for the second one. If, again, I think in terms of distributing, I have P and Q or P and R. We already talked about this one. P implies Q is equivalent to not Q implies not P. P implies Q is equivalent to not P or Q. If I have P or P, that would be equivalent to P. P and P is also equivalent to P. Not P and Q, using De Morgan's law, is not P or not Q. And not P or Q is equivalent to not P and not Q. Those are just some rules to keep in mind. Okay, so assuming here we have that T represents a true statement and F represents a false statement, then it should make sense that given any statement P, if part of the problem is true and you've got the word or, then you have to have a true result. Because remember that with or, only one of the parts must be true in order for the whole statement to be true. So it doesn't matter whether the first part is true or the second part is true. If you have a true portion to the statement, the answer will be true. The same thing with and. If either part of the statement is false, then the result will be false. So in this situation, no matter what P is, whether it's a true or false statement, because of the and symbolism, since the second part is false, the result has to be false. The same thing on this part. If P is true, then the negation of P would have to be false. And I could do the same thing and say if P is false, then the negation of P is true. But either way, with the or statement, one of them has to be true, therefore the result has to be true. And the same thing with the and statement, since one of them has to be false, the result has to be false. Okay, so let's look at the circuit for this problem and make sure you see how it works. Remember that what we talked about is that if you have the word and, if you have the symbol for and, you have to have a series circuit. So you'll notice that the P and the Q are on one level because that is a series circuit right in there, and you're using the word and. So this is our and portion to the problem. Now what we have down here is we're showing, using our rules, that P implies Q is the same thing. Remember what we talked about is not P, or the negation of P, or Q. So remember what we talked about. P implies Q is equivalent to not P or Q. So what we've done is we've converted this part of the problem into not P or Q. This is our P portion. This whole thing would be the Q portion. So now again, the and symbolism means that I have a series circuit. So I have the series circuit across the bottom. But the or symbolism, the or symbol means that I have to have part on top and part on bottom. So this part went on top and all of this went on the bottom, and it's a parallel circuit. And so that's how I ended up with this circuit that you see here. I hope this helps. We're working on the videos. If you have any problems or any questions, just let me know and we'll work on getting you cleared up. I hope you have a good week.